thought we were going to be last, okay, and we just didn't want to go through the regular dog and pony show like everybody else had, okay? So we figured we would not do that, okay? As it says here, dog and pony show is verboten, okay? That means not accepted. So, here we go.
So our project is real-world application of distance problems. Judy Hutchinson, Jefferson High School, and Myron.
Prchal, Jefferson High School. Okay? We'll keep that there for a little bit so you can write down all those words there. There's 6 of them, a little small one in between. Come on, Brett. I know you're a math teacher, you can't spell, so try to get it right. Did I spell them right?
Is my computer in the way of that? What's that pirate?
Okay, everybody got it? The important people have it, right? Okay, here we go. Participation information.
Oh, wait.
We got Judy Hutchinson, okay, and Myron Prchal. Oh, we better switch over here. There we go, got it. Okay, well, we know we had the right spot there. Okay, and
I teach Algebra 2 and Geometry. Most of my geometry classes are co-taught classes.
last year I taught Algebra 1. I'm going to be teaching it this year again, and I'm also going to be teaching Algebra 2. Last year I taught honors geometry. Okay.
So with our lessons, we've made modifications.
What happened? Hold on, we gotta. Did somebody turn the speakers off?
You gotta plug it in.
Did you? Your sound is
Check
down.
your volume.
Did you ever turn
Oh,
the
we
sound
gotta
down?
go. The technical problem here, guys. I gotta go back. I'm sorry.
No, they never did give us anything. There you go.
Too bad.
Okay, there you go.
So that's better. You get the drum.
Yeah, you got that? I'm afraid you got the drum.
So our mentor
go over?
was Harry
No,
Spencer.
you were just right. I would have
He
given you
was
the...
in TAPS, Terminal Area Precision Scheduling
See?
System. And basically what we're going to do to honor his time was, in our lesson, simulations, routing, and mapping, and then collecting the data.
I have to say, he's the only person I know who is actually a 42. Okay? So here we go.
What we're going to do, it's going to be distance, rate, time problem. The students are going to start with designing their own aircraft. They're going to test them or play with them. They're going to test, we're going to also make gliders. They'll test those. Then they're going to modify things by what they've learned. And we will go ahead and move on to the next slide. The prerequisite, it's for Algebra 1 classes. Technically, this could go down, and I could see this working really well with Ben and John's lesson. You could incorporate it with the math teachers, and when they make their aircraft, then they can test the distance, the rate, and the time, and learn that stuff. So we said Algebra 1 courses, you could modify this down to the middle school very easily. We made some adjustments or modifications for geometry.
In our lesson plan itself.
What we want the students to be able to do, they should be able to measure using a ruler, divide, and measure time with a stopwatch.
Okay.
They're going to work collaboratively in teams, find the average rate, keep accurate records, find the distance between two cities by measuring, map a route between two cities. They're going to operate smart skies. They're going to calculate flight time to a given city using their data, compare and contrast experimental data with the simulated data. We're also going to change scale, because if we're going to map routes on maps, you know, it always says 1 inch equals 50 miles. So they're going to have to know how to do that. And compute the optimal cost for air flights, or it's a traveling salesman property. And the last thing we want to do is have one. Here's
we do have our, these are mathematics NCTM standards. They're all listed here. You can read them if you want, but you probably
I was surprised when I went through them how much we've got: algebra, geometry, measurement, how many standards this really, out of the 10 days, it really pulls And we are in Illinois going to core standards, Common Core. And so we look the Common Cores up, and those are the Common Core standards that we also get. So the first day. We're not really going to tell them much. They're going to think that it's a free day, actually. They'll walk in, and we'll give them a sheet of paper and say, okay, go ahead and make yourself an paper airplane. And after they have their paper airplane, we'll take them out to a testing site. Whether it's down, we have an open commons area, or whether it's outside. You could modify the lesson that way. And we're going to have 3 things we want them to test. Distance, so we'll have them throw it as far as they can, and we'll have them mark their spot. Speed, so speed will mark a distance 10 feet away, and they'll throw it to their partner and make sure we clock it. And accuracy, we will have a rectangle mapped out on the floor, and they'll get 10 tries trying to see how many they can get in the rectangle.
Similar to what we did in class ourselves. And then also, like in the beginning, our opening activity, they might have say, tell us what you think you need to make a good paper airplane.
Yeah, and then before we go out and test it, we get everybody show their airplanes and predict which one do you think will be the most accurate, which one. And after we come back in, we will actually review the data and see which one did fly the farthest, which one was the fastest, which one was the most accurate. Day 2, we are going to do gliders. We're going to do the FPG, the foam plate glider. And we're going to have the data sheet that they actually play with the elevators, the rudders, the ailerons, and find out what do they do. So they're going to have to predict before we go up there, what do you think this does? They'll write down their predictions. They'll actually go out, they'll test it, and then write down what it actually did. If we went outside to test these, we could do, again, it's a day 2, so I don't think you can do a test inside or a test outside. But if we had time, we test them inside, then test outside and say, what, did they fly the exact same? Why didn't they? And have the kids answer those questions.
What we also would do is we would, with the kids, we show that video we saw on American or Academy of Model Airplane Association, I believe, about the glider also.
After they've picked up their data, then we come back and actually show a video. This is what the rudders do. Day 3, they're going to modify it.
Pimp my ride.
So we will come back with, instead of styrofoam plates, we will have plastic plates. We will have hefty plates. We will have paper plates.
Cardstock, shiny paper, tissue paper, and just regular paper.
So they will be able to make an airplane or a glider out of whatever they want to, or take their existing glider and make modifications to it to see if they can make it better, make it more accurate. See what kind of different things they can do to their airplane or their aircraft to make it more efficient. And if they have any ideas, we'll have all kinds of different materials for them to adjust their aircraft with. After they have made their modifications, we will take them back out to the same test site that they did the first day, where they test speed, distance, and accuracy, and we will compare and contrast to see if they did better on the first day, before they knew anything, or better on the third day. Day 4. Day 4, we're going to take their choice of aircraft. So far we've made 3 aircraft. Day 1 was the airplane, day 2 was a glider, day 3 was Pimp My Ride. They're going to pick whichever aircraft they want, and we're going to find average distance. So we'll take them out, place 2 cones 10 feet apart, and they're going to test flight 10 times. And write down the times. They know the distance is 10 feet.
They'll be in pairs, and somebody have a stopwatch. Okay?
They'll have a data sheet that has the distance written out as 10 feet. Each time they throw their aircraft, they will write down the time for 10 trials, and then they will have to figure out, how can I find my rate, because I have distance and I have time. We will probably give them this equation, D equals R times T, and hopefully they will be able to figure out. All I have to do is divide to figure out my time, or my,
Right.
yeah, my rate.
But you know how high school kids are, and there's no numbers.
So we will do that, and then we will talk about how to find the average. If you have 10 total, how do we find the average? Then the next thing we're going to do is we will actually have them map a route. We will set up 2 courses. And this can be done in an open space, or it can be...
And we're just showing you, you know, the mapping here. So let me go to the next slide. Okay, this is what we're going to set up 2 courses. And we have an area called the triangle. That's the triangle. And what we would do is we create 2 courses approximately 50 feet apart. And they would have to fly from one end to the other end, okay? And then the same thing here, 50 feet apart, but then they have to fly around the obstacle, okay? And the idea is if they, okay, I'll show you the next slide. The idea now is an example of what a kid might do. On this flight, he flew it here, he stands there, and he measures the distance from where he started to there, and he has to throw it again. He's making adjustments as he flies, because he's trying to get down here. And then we add up all the sides. It took him 98 feet to go 50 feet. Now the same thing over here, but now anything on the other side of the triangle is a crash zone. So if they land there, it costs them 10 feet extra. And the same thing, they fly there, and this person took 180.
And some things we talked about is, before they even started, we'd have them predict, how close do you think you can get to 50 feet? So if it's actually 50 feet, you know, we might have some kids over there, I'm going to get there in exactly 50 feet, or it might take them 60 feet. I called this like my non-stop route, but this, if you put another cone up here, you could say this is one stop. If you're taking an airplane flight, the triangle could be your no-fly zone. So, and this is the student worksheet where they have to map out, if my plane goes over here, I got to draw this, I have to measure this distance, and then I have to record it. Then they're going to pick it up, they're going to fly it again. So they actually have to put their data down and show me the route that they flew. And that relates to when we were in the lab, and we'd show them how it related to what we were doing. Is here's the routes when they were doing the simulation. And sometimes we have to go off course to make.
Yeah, Jimmy took all the flights that he had there and plotted it in the data here. And what we saw is step by step, all of it happened. Here we say, for some reason, this guy did a go-around. He just made a loop. And here he went off course, and this is your go-around, okay? So they're going to have their own data, not as sophisticated as Harry's, but it is there.
After we've done the experimental route, where they're actually throwing the planes, now we're going to actually go to a map, and we're going to say, okay, you're going to fly from Chicago to LAX. But there's places that you can't fly over. There's special use airspace, or the no-fly zones. So they're going to measure the, we have the next slide where it shows the...
Okay, well, this is our sectors, and just like you guys had there, we have the names of the sectors. We show them all these sectors here like this. What we have the next slide is, I want to let them see the United States with the sectors. And then this one here, you don't see the United States, you just see the sectors. And all those yellow spots are special use zones, airspace. And so we'll have them fly, I think this is Chicago, from here to LAX.
And avoid those special use airspaces. They're going to have to take their rulers, put it down on the paper, map out a course that they're going to fly, measure the distance, and then if it's 10 inches, they have to take the 10 inches, convert it to miles. And we are also going to use, we haven't left the average rate that they found with their model aircraft. They're going to use that average rate, how far it took, and figure out if they can take how long it would take them to actually get to LAX from Chicago. The next thing we're going to talk about is we just did the map. And on the map, they draw straight lines. But when we fly in the air, we talk about, what do you know about the Earth? And the Earth isn't flat. So you can't draw a straight line, really. When you fly, it is a circle. So there's this thing called the Great Circle Route. And in this internet zone, if they wanted to know what...
Let me get you up there. Hold on.
I can do that.
Okay. I can also do it here.
I know, just don't play anymore. If they want to know what the code was for Chicago, what the airport code is, they can type in Chicago, and well,
You want to go to airport information? Oh, there you go.
okay. So it'll give me Chicago. We've got a bunch of different airports in Chicago.
We have here in Rockford, they call it Chicago Rockford International, RFD.
We have O'Hare, which is ORD, and Midway, which is MDW. The other thing they can do on this is they can plug in a route.
So if they know the call letter, you're going to go with the, yeah, if you know the call letters where you want to go.
I can say I'm going to go to or Chicago to Los Angeles. Well, let's go to San Francisco because that's what we did. And I can say, okay, I want to see a map of this.
Click on here for the map. No?
See where it says perhaps you want
Yeah, okay, if I click on that. Sometimes it'll go straight
Yeah.
there. And then it shows the route, and then we'll be able to point out to them, see, it's not a straight line. It's got a little bit of an arc into it. Also in this, the farther you go down,
I can do that here.
okay, it gives you how far is the real distance that you would fly.
Airtime with this great circle route.
They could, there's a place where they could put in how many knots they want to fly and things like that. But then we could compare, or we will compare, the Great Circle route distance to the distance they found on the map. So they have something else they can compare and contrast. We'll ask them before we do this, which one do they think is going to be greater? Is the straight line shorter, or is this arc shorter?
We'll ask them before we show them this.
And then even after we show them this, they probably, well, they might have their data out, but so they have an idea of we actually fly in a curve and calculate. I'll let the computers do this because this is pretty, there's a lot of math involved in that, but there's a lot of things they can find from this website, and the questions I ask on their data sheet will be investigative. So they have to look and explore the website in order to find some of these
And we
answers.
can show them to Tokyo how the curve is greater and stuff like that. You want to put Tokyo in there? Let me get up here for you. Going backwards. Put TYO, I believe. 4D dash O.
TYO,
That's what I said, didn't I? Yeah.
the ORD.
So they can really see the arc there. And they say, well, wait a second. No, we just go straight. But
And they could, I mean, you can put even more routes in, it'll jump around if I want to come back.
LAX?
Yeah. And then come back to LAX. So I didn't do it in the right order, so I'd have to play
You
with that a little
play
bit
with
more.
it.
But it'll show you all kinds of different routes.
Okay? Oh, okay? And that's the website if you want to get this.
Then we go to the air traffic control part and talk about, you know, we've already talked about the routes, but smart skies, about how we have convergence zones, we have sectors we have to deal with. And the first day, we'd spend 2 days on smart skies. And the first day, we'd give them the basic directions on, here's things, what you can do.
Yeah, what we would do is show that introductory video, which looks like a video game, and you guys saw it, and where the kids really have hula hoops around them, and just like you were doing with the kids, they'll be looking at that, and then we're going to let them play with the smart skies.
So they play with it at first and see if they can figure it out on their own. What can they do? Because video games, actually I start out the lesson asking them what video games have they played, do any of them involve airplanes? If they do, what are they? And introduce this kind of like a little video game for them. The second day we'd actually ask them, how did they think they did the first day? Did they get the optimal, you know, hit their target time? And if they didn't, we'd go back and we'd teach them there's a video that goes along with it that goes through, this is what they're doing. You reduce speed, because it was 600 knots, how you reduce speed and things like that to try to help them out. And then after we've had that discussion, they go back on the computers and see what they can do.
So here we have this great salesman problem. You doing click on that?
Yeah, not yet though.
Okay.
And then we're going to end our lesson with the traveling salesman problem. And it's basically going to be an assessment that encompasses just about everything we've covered. So the problem starts out, you're going to start in New York. And your boss says you have to hit 3 cities and you're going to end up in LAX. So we don't care what cities they hit. I give them a list of 5 cities to pick from. And they have to get there in the shortest amount of time. And their boss is going to pay them $1,000, let's say $1,000. What they have to know is they can fly at different rates to different cities. So let's say they go from New York to Seattle, they can fly at 600 knots. If they go from New York to Atlanta, they can only fly at 540 knots. So that which path is going to be better? They have to hit 1 city in the north, 1 city in the south, and the 3rd city is their choice. So of the 5 cities, I've got 2 set up, I think 3 in the north and 2 in the south. And they can pick 1 in the north, 1 in the south, 3rd city is their choice, then they have to fly into LAX. So they will map out the route that they think is the shortest. So for example, sure, go ahead. They're going to use the Great Circle route. I'll have it all written out on a sheet. We didn't copy that. But that says these routes you can fly 600 miles per hour, these routes 540, and these routes 480. They can type into here, let's say they're going from JFK.
Move the mouse.
Let's say they're going from JFK to MPL.
Minneapolis?
I don't think I flew into there.
ATL?
ATL, Atlanta. So we go there, and they find distance. And they could compute, okay, they'd know how much, their distance is 760. If I can fly 540, how long is that going to take me? They put that on their data sheet, and they create their route. They could do every single possibility if they wanted to.
Do all the cities, check it out.
For cost, the cost aspect of it is their boss says, okay, $1,000 for everything. We said it's going to cost them, I think it was $5 for every 50 miles they flew. So then, are you going to get paid? The quicker you get there and the less time it takes and the less miles you cover, the more you get out of that $1,000. If they fly to Seattle, back to Atlanta, and they choose a poor route, they're going to use up all their money. So it incorporates money plus the distance, rate, and time.
Okay.
Our assessments, just about every day we have some kind of data sheet, record sheet that they have to record what they've done. Smart Skies has an assessment in there. Traveling Salesman was one. Also with with the Smart Skies, there's a tic-tac-toe assessment that I made up where it just has distant rate time problems, and it's just on a 3x3 grid, and the kids have to pick 3 problems, and just so they make tic-tac-toe. So I don't care which 3 problems they choose. They can choose the 3 problems here or diagonally, but I tried to set up the arrangement so they have to have one easy, one that's a little bit harder, and then one middle level problem. Next steps. We will use this really early in the year. Whenever one-step equations comes up, we will do that. I kind of look at this as baby steps with our kids. when we were going to do modeling and simulation, if I just said, okay, draw me an aircraft, or make me an aircraft, design me this, being hit with a lot of resistance, because they're not quite sure where to start, how to start. So when we started to design this, we kind of thought, well, everybody knows how to make a paper airplane. They won't resist that so much. And if we kind of bring them into this slowly, I think they will respond to it better, and they will think they're playing more than they are learning. So that's why it's paper airplanes and things like that. And hopefully later in the year, as we get going and we get them used to modeling and simulation, we can start with a harder problem, and they have to struggle with it a little more, and they'll be more willing to think about it because they've actually done the easy ones. How we're going to use this, it's like I just said, we're going to use it. I think it's going to get harder. We start out with the easy ones, and then it's going to be by the end of the year, okay, now you go ahead. Here it is. You know how to do this. Struggle with it. Figure out the answer and bring it back to me. Okay? One of the big things that this conference, this internship has done for me is all the different websites out there, all the different resources that we've been exposed to. I think every teacher that I ever come across is going to be amazed by what's really out there. I had no idea Smart Skies existed.
Or the NASA web. I mean, you hear about them. I mean, like, that's why we're here, because you want us to get that information out to the rest of the teachers, okay? So we can, get the STEMs going. So we're going to show it to everybody we know, okay? And like that.
And you've heard NIATM, we've already got hopefully we'll have this set up by the time we get home, a conference. We don't know about kids yet. Other teachers in other states, I have a niece that teaches geometry in Indiana, and I've been sending her just about everything that we cover every day. I'm sure she will try to get into this next year. She will definitely try to apply and see if she can be accepted. So we're going to tell everybody and anybody who listens. So, again, thank you so much.
Any questions?
First of all, thank you.
Okay. Any questions?
I have some suggestions. One is that, if you try to explain great circle, you'll have to explain latitude, longitudes, and then you'll have to tell them the basic idea that there are 2 points on the surface of the Earth. And if you take a plane that goes through those 2 points and goes through the center of the Earth, the arc that you get is the great circle.
Very good.
So, you have to explain that to children, because I think they can plug in the numbers, but they won't quite know what is happening.
We could use an example. We could take a melon or an apple and
Right.
slice it and show the
What
arc,
the great circle would be.
and then we could. That's a good idea. Thank you.
So that is one thing. The other thing I was thinking was that you could also, give them like shortest route kind of problems. So if you create a network of links, and then you could basically ask the kids, and you give all the locations of the nodes, and then you ask the kids to kind of start from the destination. So the problem is you have to go from one location at one boundary to the other location at the other boundary. Is there a systematic way of finding what the shortest route is? So basically they'll have to see that you start backwards. This is like the dynamic programming approach. But you figure out what the length is, because they know if you know the 2 points, they compute the distance. That, I think, Algebra 1 kids know how to do that. So then, if you know that distance, how do you move backwards? And at each location, can you make a decision such that you get the shortest, you will get the shortest path. You follow the shortest path from the destination to the origin. So that is one kind of problem. The other is you could give them problems which are like conflict detection problems. So you could say that if you are going along this line and you have a location here, you have a certain speed, and it takes a delta t time, a small time, like 5 seconds or 10 seconds, you can get to the next one. Right? So if there is another airplane that is going this way, so you could, so let's say it's going faster, so it will be here. That very time. Compute the distance between us and see what the distance is. As you get closer, you will see what the shortest distance is. Between then the distance will increase. You can also do things like if x, or if x is equal to x naught plus some dx times t and the what. So this is for the first airplane. So you will get two equations for the two airplanes and find out at what time they come through this, so they can just solve it. They can solve a system of two equations. Things of that nature.
Thank you. Thank you.
Okay.
Any others? Okay.
I just would like to make a quick comment. I like the way you progress them through it rather than just throwing a whole bunch at it. I think particularly since you indicated you had this wide range of backgrounds and abilities, and some in Algebra 2 who hadn't passed Algebra 1 or geometry and so on, I think that's a very wise way to scale it up for them.
Then the other suggestion I had is Ben and John showed a video of air traffic control, or people talking about air traffic control. I would like to see Harry and Tom put together a video of talking about air traffic control that we could actually put in our classroom. I think it would be great.
Challenge.
I had one comment. I thought, and I don't know if you all do this, but I think it is so important because you're actually teaching the scientific method every time you say make a hypothesis, predict, and subtly getting them into, you know what you guys just did? You generated a hypothesis, looked for data, and validated it or created a theory out of that. I mean,
And that's what I got from Bob, is I could say that when you have your chart, I thought I should be incorporating this. This is what we're doing, but we're also doing
Right.
math.
I was going to have her steal that so we could show it too, you know, but.
Oh,
No, I know.